Additional psychophysical tests of the V1 Saliency Hypothesis, Part 3, testing a zero-parameter quantitative prediction. We have seen that in a simplistic V1 without any neurons tuned to both color and orientation, V1 Saliency Hypothesis can quantitatively predict the reaction time for a double feature singleton that is unique in both color and orientation, given the reaction times for the corresponding single feature singletons. No free parameters are needed to reach this quantitative prediction. A whole distribution of reaction times can be predicted accordingly. However, we have also seen that if V1 does have neurons tuned to both color and orientation, then this race model equality no longer holds, but should be replaced by this inequality so that the reaction times are likely shorter than predicted by the race model. This inequality means that this reaction time can no longer be predicted precisely in its quantitative value. We have pointed out that the race model can hold when the two feature dimensions involved are color and motion direction. This is because experiments have found few V1 neurons tuned to both color and motion direction. One may question whether this can be certain that neurons tuned to both color and motion direction are absent in V1. Whether a neuron is found to be tuned to some features or not may depend on the observation criteria and is also likely to depend on the statistical properties of the visual input environment. However, by adding one more requirement that these neurons would have to be tuned simultaneously to all these three feature dimensions, color, motion direction, and orientation, then one could be more certain that few such neurons are present in V1. Then one can extend this race model involving two feature dimensions to this one involving all the three feature dimensions. Each of these three reaction times are for single feature singletons, unique in color only, motion direction only, or in orientation only. Each of these three reaction times are for double feature singletons, unique in both color and motion direction, or in both color and orientation, or in both motion direction and orientation. And this is the reaction time for the triple feature singleton, unique in all the three feature dimensions. This is a schematic of a single feature color singleton visual input. Each bar is not only colored and oriented, but is also moving. An arrow indicates the direction of motion, so here all the bars are moving to the right. All the bars are oriented clockwise from vertical, but the bar that is the odd one out is unique in color only. This is when the odd bar is unique in motion direction only, and this is when the odd bar is unique in orientation only. These are for the three types of single feature singletons, and these are for the three types of double feature singletons. This singleton is unique in both color and motion direction. This one is unique in both color and orientation, and this one is unique in both motion direction and orientation. And the triple feature singleton is unique in color, motion direction, and orientation. Once the reaction time for the single feature and double feature singletons are measured, we can predict the reaction time for the triple feature singleton by this race model equation. So for example, if these are the respective reaction times for these three single feature singletons, the minimum among these reaction times is 0.58 seconds. And if these are the reaction times respectively for the three double feature singletons, and the minimum among these is the 0.45 seconds, then we can apply this race model equation and we get this equation. With this minimum for the 0.58 second here and with this minimum for the 0.45 second here. And so we arrive at a quantitative prediction of this reaction time as 0.45 second without any free parameters. Since reaction times are statistical, we measure the respective distributions of the reaction times for the single feature singletons and for the double feature singletons to predict the distribution for the triple feature singleton without using any parameters. This is an example prediction compared with the experimental data, which is the actual observed distribution of the reaction times. The prediction matches the data well statistically, and this example is from data by a particular human observer. This test of the V1 Saliency Hypothesis can be repeated in other observers, and these observers differ from each other in their distributions of the reaction times, but in each of them, the prediction matches the corresponding distribution. Let's remind ourselves that for the color orientation double feature singletons, the reaction times are shorter than predicted by the race model. And this is because V1 has neurons tuned to both color and orientation. In contrast, because V1 has few neurons tuned to all these three feature dimensions simultaneously, the prediction here matches the data. However, higher visual cortical areas downstream from V1 along the visual pathway do have many neurons tuned to triple conjunctions of features. So if they contribute to the visual saliencies of the singletons here, we may observe these reaction times shorter than predicted. Now, since the data confirm the prediction, this is not only a support to the V1 saliency hypothesis, but also suggests that V2 and other higher visual cortical areas do not contribute to the saliencies of these highly salient singletons that pop out to attract our attention so strongly to give such short reaction times. Since quantitative predictions without free parameters are relatively easier to falsify if the theory is incorrect, this confirmation of such a prediction provides a strong support to ViSH.